this first session of the day. Sorry for the delay this morning. In case you were wondering, snow is not a very common event in the city. So if you are from the East Coast or from a colder place, you might find this somewhat entertaining. But yeah, lots of people have to commute into the university from places that have far more snow than here. All right, so this is a very exciting session, and the topic is, well, roughly communication and coding. So this is really in the true spirit of ITCS. So as you're going to see, there's going to be a diversity of topics, and a lot of it is going to be about looking at old problems in a new way and making connections to other problems and so on. So the first talk, so I rearranged the order of the talks as I'm going to describe them just to make a little bit more sense thematically. So the first talk is going to be about two different topics that share the same acronym, namely MPC. So I like to think that the authors did this intentionally in choosing their research direction. So your MPC means both massively parallel computing and multi-party computation. So massively parallel computing here, it's a computational model that somewhat abstracts framework for distributed data analytics. So you have a bunch of nodes with limited memory. They can talk to each other. They each get a chunk of the inputs, and you want to perform some computation. And now you would like to compile such a program into a secure one by preserving its complexity. Secure meaning that you want to resist the corruption of a subset of the nodes in a cryptographic sense. And so the solution is kind of elegant in the sense that there are two steps here. And the first one is algorithmic. So even if you're not a cryptographer, it's really about establishing oblivious communication for such algorithms among the nodes. They're trusted. And then you add a very fancy crypto on top of it to get the security for multi-party computation. And so on a similar topic of compiling is actually the third talk that Yael is going to give. And this actually revisits the classical problem of interactive coding. And as you know, or most of you know, so here the problem is to compile a two-party protocols into one that resists adversarial errors. And generally, the complexity metric here is to preserve communication complexity. But if you actually look at the real-world protocol, communication complexity is not the only important parameter. In many cases, you can afford bandwidth more than you can afford rounds. And the prior solutions, they really only care about communication complexity. You can add rounds as you like. And so here they give a first protocol that is nice with respect to round complexity. In the sense, there's only a constant blow-up in the round complexity, and there's some other properties. And so moving on again in the context of distributed protocols. So Luca is going to talk about two classical problems, consensus and broadcast. These are two of those problems where you would think we should understand by now. There are still a lot of very open questions. And in particular here, the setting is that of general networks topology and very simple communication models, so think gossip algorithms. And consensus, again, is every party has an input, and you want to agree on one of these inputs. And broadcast is one single party has an input, and everyone should get that value. So it's kind of easy to see that if you have a broadcast protocol, you can get a consensus protocol. But now here, the question they ask is in the other direction, at least the first question they ask. And they show that you can get some sort of weak broadcast, which is enough for lower bounds. And also, somewhat even another exciting part of the paper, which maybe is the biggest part of the paper, is they also look at very simple communication model which are noisy. And that's actually some nice inspiration from biology. So you have a gossip model where you can send a single bit at a time, and this bit is noisy. And you want to see, again, what you can say about these problems. And again, changing topic once again, the second to last paper of the session, this is a coding part. We'll go back to the classical problem of least decoding. And so far, when you think about least decoding, usually you think about this in the Hamming model, where you can adversarially flip some of the bits up to a certain threshold. So what the paper does, and I'm not rendering entirely justice, it's an 80-page plus paper, which really does a comprehensive study. But what it does is it considers a general model of deterministic channels and tries to find necessary and sufficient condition for least decoding and generally studying the problem there. And it's kind of nice because it connects a bit of more of the viewpoint from information theory and looking at general channels with what is more of the TCS view here. And then the final two topics, again, all different type of things. So they're sort of, the final two talks are unified by looking at problems on graphs and making connections to problems in communication, broadly defined. So this is the second paper by Nathaniel. So he's going to talk about the problem of labeling graphs. So this is So it's an elegant question where you are given a graph and you want to assign labels to the individual nodes such that you can decide some pairwise property of vertices just by looking at labels. For example, you just look at the labels of two vertices and you want to say, are they adjacent or not? And now here, the connection with communication is that, so he introduces a model of simultaneous message passing that he calls Universal SMP, where different from the original model here, the referee that produces the output doesn't know the function being computed. So think of the function as being part of the input. And now you want to get such labeling scheme from such protocols, and he gets new ones by using techniques from communication complexity to build such protocols. So here you're using communication complexity for upper bounds as opposed to lower bounds. And again, a completely different thing for the final talk, but still some connection with graphs and communication. So here the starting point is fault tolerance. So what they're interested in here is the problem of building fault-tolerant subgraphs. So you want to essentially get a subgraph which, by removing a bunch of edges from an original directed graph, such that if some of these edges can fail, you can decide still connectivity just by looking at these subgraphs. And this is a problem that has been studied in a few papers. We know upper and lower bounds for general graphs, but here the question is, what can we do in terms of improving parameters, in particular dependency on the number of nodes for specific classes of graphs. And again, here the connection is with kernelization and parameterized complexity. Okay, so with that, I'll just let Wei-Kai start with the first talk.
Thank you for the introduction. This is a joint work with Hubert Chung, Chung, and Elaine. In this work, we aim to make secure parallel computations. There are many models of parallel computation. And recently, due to the development of physical hardwares like clusters and data centers, people moved on to this massively parallel computation model, or MPC. This is the model in this work we work on. So in MPC model, there are some number M of random access machines. So each machine is like our laptop here. And every machine are totally connected through the network. And each machine has a local space constraint S, where given some input size n, the local space S is just a small polynomial of n, which is by small polynomial, it's n to the epsilon for some small fraction epsilon. So one machine cannot read the whole, or do not have the space to read the whole input, and we need some large enough number of machines to jointly read the input. And the algorithms in MPC model proceeds in the following way. At the very beginning, the input is split into these M machines, and then every machine performs local computation using its own space constraint S. This local computation includes the next step, computing which message to send to which receiver, and in the next step, we really send messages. Also, there is still the space constraint in this communication, so we suppose every machine can send and receive at most S speeds in this step. We call this a run, and the MPC algorithm proceeds run by run until at some point all the machines jointly halt and output the result of this computation. And the main metric of MPC is the number of runs this algorithm takes. Okay, and a brief comparison with another parallel model, PRAM. In PRAM, there are larger number of processors, but there's only one single shared memory or storage. And PRAM counts the complexity in the number of parallel steps. When we discussing the algorithm for same problem like sorting, MPC algorithms use less number of runs than parallel steps in PRAM because there's the benefit of local computation. This is one of the reasons people work in MPC. And in this work, we are saying if there is a good reason to work in MPC, then by the same reason, we should also consider the security for, in MPC model rather than RAM model. So this is the main question in this work. We want to know how to make an algorithm in the MPC model secure and what will be the cost. Like my previous slide showed, many MPC algorithms consume only constant runs, so we don't want the cost too much in the number of runs. And to answer this question, the very first step is to define what does it mean by a secure MPC algorithm. In the field of cryptography, there are many different models of attackers, that's different adversarial settings. And we borrowed many ideas from the field of cryptography, and in the field of cryptography, MPC usually stands for secure multi-party computation. And in this talk, I'm not going to use CTI. I'm going to use only the first MPC to avoid the confusion. Okay. So in this work, we proposed two scenarios, two adversarial models. In the first scenario, we consider the adversary is only eavesdropping on the network. So the adversary sees every message on the network, and they want to learn about secret input, say mythical record here. In our second scenario, again, there are secret input, and the adversary is additionally allowed to corrupt some machines on in the MPC model. So in this diagram, the two adversaries can totally see everything on the two machines, and they want to learn the mythical records from the other three hospitals. Both scenarios are very practical. Like in the second scenario, by government regulation, one hospital should not learn the secret mythical record from other hospital. And in both scenarios, we show the positive result. In the first scenario, the cost to defend such an eavesdropping adversary is only constant factor Blowup in the number of runs and also in the space each machine consumes. In our second scenario, the adversary is stronger, so we can still achieve constant factor Blowup in the number of runs, but now the space suffer a larger Blowup in terms of the security parameter, the kappa here. Fortunately, it doesn't depend on the input size. For the interest of time, I'm going to show the construction of our first scenario. So in this scenario, the adversary is eavesdropping, so a standard technique is just to encrypt every message in the communication, but that's not enough because the sender and the receiver information can also depend on the input. So adversary don't need to learn or see the input, the payload of the communication, just the pattern of the communication is good enough for the adversary. And so we need this abstraction that's an oblivious routing protocol or algorithm that's capable of sending messages to the prescribed destination or prescribed receiver without revealing to the adversary the prescribed receiver. To construct this routing algorithm, we use a well-known network, butterfly network. The construction is very simple. It's just a recursive construction. You put 2 copies of butterfly network of half the size, and then for every pair of nodes in the 2 halves, we switch the corresponding pair of nodes, and that's already a butterfly network of double the size. This butterfly network has a very nice property that for any pair of input and output, there is a very easy to compute path exists in this graph. So using this graph, we can construct our routing algorithm in 2 steps. In the first step, we send our messages to a random intermediate node that's totally random pick and uniformly chosen, that's unrelated to the prescribed receiver. And then in the second step, we use another butterfly network to send from this intermediate random shuffling to the prescribed receiver. And using a simple chain of bound, we can easily show that with high probability, the load in this protocol, for every edge in this protocol, the load is transmitted by a small amount of messages in this protocol. By small amount, I mean a constant times the expectation. So in order to hide the communication pattern in this protocol, we just need to flood every edge with this upper bound of messages with dummy or real messages. The only problem here is the number of layers in this butterfly network is logarithmic in the number of machines. And that means logarithmic number of rungs in our MPC algorithm. So there is a quite straightforward fix to this problem. We just need to merge several layers of this network into one single layer. Like in this diagram, we can merge 2 layers into 1 layer and increasing the degree of this network to 4 here. And that will reduce the number of layers in this network to 1 over epsilon by as a cost of degree, increase the degree. But here, every node in this network has a local space S, so we can afford a S degree butterfly network. That means constant number of rungs in our protocol, and that will solve our problem of routing. So to summarize, we can compile a MPC algorithm into a secure one. And in a weaker adversary model, the cost is just constant blowup in rungs and the space. When there is a stronger adversary that corrupts some machines in our MPC algorithm, then we need the crypto assumptions, and we can only tolerate a third of corrupted machines. That's it, but I guess I have some more time. 1 minute, okay, just 1 slide. So In our second scenario, the result requires cryptographic hardness assumptions, and there are still many open problems here, like can we weaken the cryptographic assumption or increase the fraction of corrupted machines? So most of these problems are still open, but we showed a barrier that if we can totally remove the cryptographic hardness assumption, then we will get a better secure multi-party computation in crypto. So that would be quite hard to improve. Thank you for your attention. I'm happy to take questions.
So in the permutation routing literature, there are issues with queuing and algorithms like latent mags and route to get around long queues and so on. I'm wondering how all of those things say that traffic in the network is actually going to affect the timing of messages coming through. So you know who's sending to whom, but the timing of messages, so how do you, is impacted by these algorithms. How do you deal with the hiding of the timing of what's going on?
So, sorry. So in, sure. So in the standard MPC model, all these messages are transmitted like synchronously and between the two rounds, right?
Right, but your random permutation
Yep.
will have hotspots and so on.
Yeah, so the channel bound on the probability resolve that hotspot. They upper bound the hotspot by a constant multiplied by the expectation, which is another constant.
So there's no individual node that will receive more messages? Because the normal thing is if you do it's a random permutation.
Very good question. So yes, regular algorithm will have hotspot, but if you randomly shuffle it, then the hotspot occurs with not very high probability. Thank you.
All right, hello everybody. So I'm Nathan, and I'll be presenting today universal communication, universal graphs, and graph labeling. Okay, so what's the point of this talk? Well, we've got this field on the left of communication complexity. So in the style of Yael, the two-party communication complexity, which has quite a rich history. And on the right, something that many fewer of you have probably heard about, which is graph labeling and universal graphs. And as far as I can tell, these two fields of study are essentially disjoint. And all I want to do today is convince you that there's actually quite a lot of stuff that goes right in between these two fields, that there's quite rich connections between these two things. Okay? And in order to do that, we should first review what are those things, universal graphs and graph labeling. So a universal graph was introduced by Rado quite a while ago. And what we have is a family F of graphs, so a set of graphs. And a graph U is universal for that set if for every graph G in the family, there exists a mapping phi that takes the vertices of G to the vertices of U, so that for every pair of vertices in G, they are adjacent if and only if they are adjacent, if their images are adjacent in U. In other words, U has a copy of every graph G in F somewhere inside it, So we can also require that this mapping phi is 1 to 1, so every vertex is mapped to a unique vertex in U, in which case we call it induced universal. And so like in this picture here, we have every graph in F can be found somewhere inside U, probably, hopefully overlapping as much as possible so that the graph U is as small as possible. So the goal here is to find the smallest graphs that we can, the smallest universal graphs. And the next thing that we should review is something called graph labeling, which was also introduced quite a while ago, but its more modern form introduced by Knon, Nauer, and Rudich in '92, and further expanded upon by Peleg, where we have, again, a family of graphs F on the vertices 1 through n. And we have some function, h, that takes as input one of those graphs and 2 of its vertices. Okay, so there's a function on 2 vertices of the graphs. And the goal is to find a decoder D that permits the following. For every graph G in this family, we should be able to assign to each of its vertices a label as short as possible so that the decoder will be able to compute the function h, x, y, g given only the labels of those 2 vertices, so the label of x and the label of y. The decoder doesn't get to know the graph G, it only gets to see those labels. So it does know the family F, but it doesn't get to know which specific graph that it got. So the labels must encode some information about the graph, whatever is necessary. And here the goal is to minimize those label sizes. And what these two, as an example of the kinds of things that are studied in this graph labeling field is small distance labeling, where we fix some value k, and our function is distance k distance, where it's 1 if those 2 vertices are path distance at most k in the graph G, and 0 otherwise. And if k is equal to 1, this is adjacency labeling. So we want to tell from the labels whether these 2 vertices were adjacent in G. And an observation that connects this to universal graphs is that if you have an adjacency labeling scheme where the labels are all of size S, then that implies a universal graph for that family F of size 2 to the power of S, because we can just take the set of all possible labels as our vertices in the universal graph and connect 2 things if the decoder says outputs 1 on those 2 vertices. Okay? So graph labeling implies universal graphs. So we want to connect this to communication complexity. So we have to ask, well, what model of communication looks the most like this problem? And the answer, I think, is simultaneous message passing, or SMP, which works as follows. We have parties Alice and Bob, as well as a referee. Alice receives an input X. Bob receives an input Y. They all share this function H. Alice and Bob send a single message each to the referee, who must then output H of X, Y. And in the randomized case, we may also allow Alice and Bob to share a source of randomness. So there's some public set of random coins that Alice and Bob can both see and use to send their messages, but the referee does not get to see those random coins and does not get to see the inputs X and Y. Okay, so let's forget about graph labeling and universal graphs for a moment and just ask some natural questions about this SMP model. And the first question is, well, what if the referee doesn't know H? So the referee doesn't get to know the function that they're supposed to be computing. Or in other words, Alice and Bob receive the function that they're supposed to compute as input and must also send some information about it to the referee. Or an equivalent question that might sound a little bit more natural is, what if Alice and Bob are in some shared environment E that the referee doesn't know? So the referee should compute some function that depends both on Alice and Bob's inputs as well as this shared environment that Alice and Bob can see. An example here is, let's say Alice and Bob are both in the same city, and the referee needs to decide if they're close together, but doesn't get to know Alice's location or Bob's location, and doesn't even get to know which city they're in. So what's the map of the city? And to answer this question, we can expand the SMP model into what I call the Universal SMP model, sort of named after the universal graphs, where Alice again receives an input X, Bob receives an input Y, and we can think of these inputs as being vertices of a graph. and the graph, and they both receive this graph G from some family F of graphs, and then they can both as well share their randomness as before. And now we have this referee who's oblivious to the inputs X and Y, the graph G, and the random strings, but still must compute H of X, Y, and G. And in the randomized case, also cannot see the randomness. Okay, here's an example of a protocol in this model. So let's say F are the graphs of degree at most 5, and H of X, Y, and G is adjacency in G. So H of X, Y, G is 1 if X and Y are adjacent in G. What Alice can do is she can send each neighbor of her vertex X, all 5 neighbors, and Bob sends his vertex Y. And then all the referee needs to do is check to see if the vertex he got from Bob is one of the 5 vertices that they got from Alice. And so the cost is order log n bits for each vertex. But something nice is that in the SMP model, in the randomized model, we can compute equality of 2 things in a constant amount of communication by some random hashing. And we can do this to get a much better randomized protocol in this universal model for this problem. So we actually get constant cost randomized protocol for adjacency in degree 5 graphs. Okay, so now it's fairly easy to see that this universal SMP model generalizes the standard SMP model, because we can take this family F just to be the singleton family. So whichever function it is that you wanted to compute, that's just the only thing that's in your family F, and so universal SMP generalizes regular SMP. And I also want to claim that universal SMP generalizes graph labeling. This is just slightly more difficult to see, because communication protocol is not necessarily symmetric. So one should be able to easily see that given a graph labeling scheme, you could get a deterministic universal SMP protocol. We want to go the other way, but we want to use Alice and Bob's functions as the labeling scheme, but Alice and Bob may have different functions, as in our degree 5 example, right? So we just need to symmetrize this, and this is okay. We can actually fix this, and therefore, there we go. Therefore, universal SMP generalizes both SMP and graph labeling, and therefore we actually have something in the middle here, something that belongs to both worlds. Okay, so now let's just briefly look at some facts about this universal SMP model, kind of from a communication point of view. The first is that there's this classic theorem in communication complexity that lets you de-randomize protocols with public coins, called Newman's theorem, and we can do something very similar here. We can say that if we have a randomized universal SMP protocol, we can get a de-randomized deterministic protocol with a logarithmic factor blowup. Here n is the size of the graphs, right? So we get a logarithmic factor blowup, but we get a deterministic protocol, but this is non-constructive, similar to Newman's theorem. So this is a non-constructive protocol. And another interesting thing is that if we have a 2-way communication protocol for every graph in our family F, then we can get a universal protocol. And how we can do this is we can just say, well, for each one of these 2-way protocols, look at the communication tree, and then Alice and Bob are going to send an annotated communication tree that the referee can then use to reconstruct the protocol transcript. Okay, so from 2-way randomized or deterministic protocols, we can get universal protocols. And together, that means that we can actually use 2-way randomized protocols to get upper bounds on graph labeling problems, okay? Or upper bounds on universal graph sizes. Okay, so now we've got USMP, Universal SMP, here in the middle, and so what I do for the remainder of the paper is just to say, well, what problems do we have in these 2 worlds that we can also study sort of in a unified way in this Universal SMP model? One of the interesting ones is that in communication complexity, one of the most commonly studied problems is K Hamming distance, which I have here on the left. And then on the right, in graph labeling, it's common to study things like trees or planar graphs or universal graphs. And so I show that starting from here, we can take these graphs in the graph labeling setting and try and find these communication protocols or randomized communication protocols. Or we could take these standard communication protocols that are known and see what kind of graph labeling schemes we can get from them. So some results, the K-Hamming distance protocols, basically you can just take the existing protocols and more or less using the results about universal SMP, you almost immediately get that there's a polynomial size universal graph for n vertex-induced subgraphs of the hypercube using these de-randomization results. Or you can get a log n cost labeling scheme for computing k distances on distributive lattices. So I don't have time to go into what distributive lattices are, but for n vertex distributive lattices, you can get a labeling scheme, a constant cost, you can get a constant cost randomized universal protocol, which then implies this log n cost labeling scheme for small distances. You can also, in the other direction, taking trees from graph labeling, we can get an order k cost randomized universal protocol for computing k distance on trees. And we can get a constant cost protocol for computing distance 1 and 2 on planar graphs. And this also implies, I think, a new graph labeling scheme for this problem on planar graphs. And we can also show that interval graphs are essentially equivalent to the greater than problem in communication complexity, which means that there are upper and lower bounds on the randomized and deterministic communication protocols of log n. And so I think some of the most interesting things about this model are things that will hopefully come in the future. So I'm going to mention a few of the open problems. One of the more maybe minor open problems here is, well, I got distance 2 protocol for planar graphs. Can we get arbitrary k distance protocols for planar or even for minor free graphs in general? Communication complexity is usually used for lower bounds, not upper bounds. And so it would be really interesting to work out what are the universal SMP analogs of standard communication lower bounds. And one of the interesting things is that in graph labeling, there's the main open problem is this implicit graph conjecture, which says, do all hereditary families of graphs with small enough size, with few enough graphs in the family, have an order log n adjacency labeling scheme? And so something interesting that comes from this work is that we kind of can get a finer granularity on this problem using randomization. So in the deterministic setting, all of these hereditary graphs that are small enough would have a theta of log n adjacency scheme if this conjecture is true. So they're kind of all the same in the sense that log n is kind of the optimal that you can get. But in the randomized case, when we introduce this universal model, many of these things like planar graphs or trees get constant cost protocols, while others like universal graphs get log n size protocols. So there's more of a separation here. Some of these are constant, some of them are log n. Is there anything in between? I don't know. Or even is there anything larger? And can we even use these lower bound techniques for communication complexity to maybe even try disproving the implicit graph conjecture? And of course, this is a new model. There's many more interesting things that you could ask about this model. So I'm hoping that in the future, some more of these will be worked out. And that's everything. Thank you very much. Any questions?
Yeah, one quick question while Yael sits up. There are no questions. We just have one quick question. So, I mean, you mentioned something at the end, but just to be sure. So, you focused on graphs, but in terms of other problems where you have non-interesting, interesting positive results for the case where the referee doesn't know the input for your model. So, do you have other examples? You know, because the trivial solution in your model is, of course, to send the input over to the referee. Yeah. So, which other examples of non-graph problems do you know? Yeah.
I didn't work on any non-graph problems. In fact, I even defined the model
for graphs
here.
But it makes sense outside.
Yeah, so like any function, you just look at the function matrix and turn it into a graph, and so I kind of played as well. Graph here does a good one, but yeah, it would be more interesting to look at like standard communication problems and see what you could generalize, like generalizing the function instead of and see. Like you need to define a family of functions, so you need to like pick your favorite function. What's the natural family
Thank you.
Next up, Yael.
So, thank you very much.
Stand in front of the microphone.
Sure. Okay. Thank you very much. Thank you, Stefano, for the introduction. I wish, it seems like you did a great job. I wish you can come and give my talk. So this is joint work with Klim and Elad, who unfortunately both couldn't come, unfortunately for you and for me. So, so I'll present this. So this work is about interactive coding, which is a generalization of standard error correcting code. So let's first recall what standard error correcting codes are. So it's a model introduced by Shannon. You have a message, and it can be partially corrupted. Some of the bits can be toggled, and you want to encode it in a way that you can recover the original message. Two error models, several error models, but the main two error models that were considered is the stochastic one, which assumes the noise is random, and the adversarial one, which assumes that the noise is arbitrary, an arbitrary epsilon fraction of the bits can be corrupted. And this is the noise model that we use in our work. And more generally, the noise model that we work is not, we don't only assume that the adversary can toggle, can flip it, but he can also insert and delete bits from the message. Okay, so there's a notion of what's called a good error correcting code. And a good error correcting code is one that is resilient to constant fraction of adversarial error while blowing up the communication by only a constant fraction. And it should have an efficient encoding and decoding procedure. So this is what's good error correcting codes. We have several good error correcting codes in the literature. The topic of this talk is interactive coding, introduced in the seminal works by Schulman. So what is an interactive coding scheme? Here, instead of just having one message, we have a conversation back and forth. So Alice talk back and forth, and what we want to compile this conversation to a new conversation such that even if constant fraction of the bits of this entire conversation are corrupted, they can still recover what they would have spoken had there been no noise at all. Okay, so again, it's a compiler. Interactive coding scheme is a compiler that takes any protocol, converts it to a compiled protocol that is resilient to constant fraction of error. And resilience here means that even if there were constant fraction of errors, you can still recover the original conversation. Okay, and even here there's the notion of what's a good, this time interactive coding scheme is, and the notion is similar to the standard one, which is it should be resilient to constant fraction of adversarial error. So if the total number of bits is t, it should be resilient to some constant epsilon t bits of error. There should be only constant blow up in the communication, and it should be efficient. Okay, so efficient to compute and efficient to decode. Okay, so this is the model. Just to point out, just a sanity check, it's tempting to think that you can just apply a standard error correcting code message by message, and that will solve the problem. I want to point out it does not solve the problem because it's not resilient to constant fraction of error. Note that here, the first kind of several, actually epsilon fraction of messages can be completely corrupted, completely. So if you apply error correcting code locally in the message, it won't give you anything. And what we need here is a global mechanism of correcting error. Okay, so there's been a lot of work on this topic, trying to get optimal error rate and optimal information rate, which means optimal blow-up in communication, a lot of work on computational efficiency and on various types of error models. The point is we have good interactive coding schemes. Okay, so ones that are resilient to constant fraction of adversarial error with only constant blow-up in communication and are efficiency preserving. Okay, the question we ask in this work is, what about round complexity? This is something that was not at all discussed in this line of work on interactive coding. And moreover, not only wasn't discussed, actually all prior work assumed, they start with an assumption that the communication is bit by bit. So first they say, let's assume with all loss of generality that each party sends 1 bit, and then we're going to convert this into an error-resilient one. And moreover, there's always an assumption that we know the communication complexity. So we know we're going to communicate T bits, it's going to send bit by bit, and we want to convert this into a error-resilient version. Okay, so in our model, we want to go back to kind of the models that are mainly used by cryptography and in distributed algorithms, which is messages can be of arbitrary length, and actually round complexity is a very, very important measure that we want to preserve. So we consider what's called the synchronous message passing model. So here, again, there's Alice and Bob. Alice can send a message, it can be of arbitrary length. Bob receives this message, he sends a message, it can be of arbitrary length, and so on and so forth. And moreover, the length of the message, not only what's written in these messages, but the length of the message can be adaptively chosen. The number of rounds can be adaptively chosen. So we assume no a priori bound on the communication complexity and on the number of rounds. So, when the two of us talk, maybe you say a few words, I'm not interested, I go away. Maybe we start talking, I'm very interested, the conversation goes on and on for hours. This kind of models more realistic kind of communication. Okay, so given this, we suggest that actually what should be good error correcting code, good interactive coding, is one not only that is resilient to constant fraction of error with constant blow up in communication and efficiency preserving, but also should also preserve the number of rounds. There should also be only a constant blow up in the number of rounds. Okay? And moreover, in this setting, in our model, I think it's very important to allow insertion and deletion error, which we do. But the reason why it's very important is not only because insertion and deletion it's a realistic model, but moreover, because we allow messages of arbitrary length, if you do not allow insertion and deletion, the parties, in essence, can code information just via the length of the message, and that cannot be corrupted. So we don't want to assume that. So we allow the adversary to change the length of the message. Of course, he'll pay for it. That's considered an error. He can insert, he can delete. So this is the notion of good coding scheme that we want to consider in this work. And what we show, we construct a good coding scheme according to this kind of, with these parameters. So we construct a good coding scheme. We do not assume any a priori bound on the communication of the round complexity. The communication of the round may depend on the kind of type of Alice and Bob, and it can be completely adaptive. Okay, so moreover, in our work, we optimize the constant here. We have various optimizations, but essentially show as the error approaches 0, the blow-up approaches 1. So there's no blow-up as the error approaches 0. Okay, so this is our result. And in the few minutes I have left, I will tell you a little bit about how we get this result. Okay, so getting actually this only constant blow up in rounds, forget about the optimality, just getting the constant, any constant, requires a lot of technical hurdles, which I want to tell you about. So the starting point of this work is the work of a Bernard Hopler, which gives a good interactive coding scheme according to the prior definition, where it's bit by bit. So essentially the way it works is, in our model at least, Alice, every time you send a message, you append to it a hash of what you believe the communication is so far. And if Bob does the same. You always send a hash kind of to make sure you're consistent. So you just send the messages as you would in the original protocol, but you always append a hash of what you believe the transcript is so far. And if you notice an inconsistency, essentially you backtrack. That's the high-level idea. Just send hashes with your messages. If there's an inconsistency, you backtrack. Now, of course, this is a very, very high-level overview. First, how do you backtrack? Well, they backtrack using Schulman's idea of meeting points, which I'm not going to get into. Next question is where these hash functions come from. So you can assume there's a kind of a lot of seeds for this hash function in the sky. Of course, we don't want any sky, so we implement this, or it's implemented using delta bias source of randomness, so it can be shortened. So, but essentially the high-level view of prior work is this. You send a message, you append to it a hash, you check consistency. If it's inconsistent, you backtrack. That's kind of the high-level idea. What's going on in our case, where messages can be of arbitrary length? So first thing we need to do is we need to smooth out the protocol. So for example, if Bob sends me 1 bit, and after that I send a really long message, that's a big problem. Because what the adversary can do, he can just corrupt 1 bit of Bob, making my entire message meaningless. So if Bob says, I don't want to talk to you, now I speak a ton, the adversary just wasted a lot of, caused me to waste a lot of communication. It will blow up the communication complexity. So we need to assume that it's smooth somehow. By smooth, I mean that after 1 message of certain length, you can't have a message that's much longer. Let's say it can be at most twice as long, or at most half as short. So kind of smooth. Okay, so we do that. We smoothen out. We show how to smooth it. Fine. Then we have a serious problem. Because the smoothing is not perfect, still messages can grow kind of, as you go down, they can grow or shrink in an exponential rate. So they can grow each time by a factor of 2, let's say. Then if we found a place we're inconsistent, before you just like to erase all the things that you said after the inconsistency you want to erase. Here you can't erase it. You need to be very careful when you erase. Because what happened, because the message can grow exponentially, you may have erased, the adversary can cause you to believe you're inconsistent, even though you are consistent, and make you erase kind of an exponentially growing body of messages, which will kill you. So you need to be very, very careful when you erase. You need to kind of keep it questionable and be very careful with that. Okay, that's another thing. Finally, a really big problem we have is that in prior work, because we don't want to blow up the communication, the hash size is proportional to the message size. It can't be bigger because otherwise the communication will be super constant. So the hash was just kind of proportional to the message size, or constant in the case of bit by bit. Here we can't do that. And the reason we can't do that, actually the hash length should depend on the entire communication so far. And the reason we can't do that is because the seeds are known ahead of time, what the adversary can do, he can actually decide to corrupt a really, really long message where his entire goal is to cause a lot of hash collisions in many, many rounds. So think you have many, many rounds with kind of hashes of constant size, and you have one really, really long message. The adversary will just corrupt that with the entire goal of causing many, many hash collisions, and hence blowing up the round complexity. So you can't do that. So what we do, we make the hashes kind of depend on the entire communication in a smart way that the adversary won't be able to do that. But as a result, our hash sizes are bigger. Blows up communication. Problem. So essentially what we do, we hash the hash. So we hash the hash. Okay, that also, what do you mean hash the hash? So we have kind of an outer hash where the seed is sent kind of on the spot, not ahead of time. There's more problem that actually you don't even know what the seed length is because you don't know the communication complexity is, you don't know which delta to use. So it requires kind of overcoming many, many hurdles, which I won't have time to tell you more about, so let me just summarize. So our result, we give a good interactive coding scheme in the synchronous message passing model. We do not assume any a priori bound on the communication around complexity. And by good, we mean not only constant overhead in communication, but also in round. And we are able to be resilient to insertion and deletion error. Okay, thank you. Questions?
Yeah, so we'll be short on time, so very quick question while the next speaker sets up very quickly.
Actually, I have a question.
Okay. Yeah, you can do it while setting up.
Which is that, let's say you have a two-round protocol,
Two.
and I send like a one message bit, you reply with an n message bit.
Yes.
Then it seems that to smooth it out, it would take log n rounds,
So good.
unless
You
you
know,
make the first message longer.
You're totally right. I cheated. I don't know if you noticed, but that theorem was kind of in quote. You do have an additive log of communication complexity, which yeah. Any other, but you were paying attention. It's good, Luca. Okay, thank you.
Thank you.
Thank you. Right, so I will tell you about some joint work with Andrea, Clementi, Luciano, Gualá, Emanuele, Natale, Francesco, Pasquale, and Giacomo Scornavacca on a couple of problems in distributed computing. So the setup of distributed computing that we think about is one where there is a communication network represented by an undirected graph, where every node of the graph is a computing device. Every edge of the graph represents the ability of two nodes to communicate with one another in one round. A protocol starts with every node having some local input, and the goal is for every node to compute some function of these local inputs. There are several different models that prescribe exactly how the communication between nodes at every round is allowed to proceed. For example, in the local model, every node can send messages of arbitrary lengths to all its neighbors. In the congest model, every node can send messages of bounded length to its neighbors. We will look at a more restricted model called gossip, where every node can communicate with only one neighbor, and we will see various variants. Okay. So regardless of the model, a couple of problems that are very basic and that underlie several more complicated processes are consensus and broadcast. In the consensus problem, the goal of the nodes is to agree to some value that at least one of the nodes had at the beginning. So it doesn't have to be the majority or a plurality, just some node, some value that at least one of the nodes had at the beginning. If you just ask for the nodes to all agree to some value, then that's kind of a trivial problem, because you could have a protocol where every node agrees to 42 or some fixed number. But just requiring that they agree to at least one of the values that they had at the beginning makes the problem non-trivial. So this would be a possible good outcome of the consensus protocol. Those are a couple of examples of what would not be a correct outcome. In the first case, because the nodes are not agreeing. In the second case, because they agree to some value that nobody had at the beginning. Another basic problem, well studied in distributed computing, is the broadcast problem, in which the goal is for one node to transmit its local information to all the others. The kind of complexity measure that we will look at will be the number of rounds of the communication protocol. Okay. Now, one relation between those two problems is that if we have some way of solving the broadcast problem, we can use it to solve the consensus problem. Because one approach to consensus is for one node to broadcast its value, and then everybody agree to that value. then for sure they are agreeing, and they're agreeing to evaluate at least one node at the beginning. Actually, in the huge number of reasonable models for distributed computing, there are some models in which, the part in which everybody decides who is the node that is going to broadcast is actually a bit non-trivial. So you cannot always have this reduction. Although in general, whether through this reduction or through sort of using this idea and kind of getting around the issue of how to pick the broadcast node, it's always the case that there is a way to solve consensus that is no harder than the best way of solving broadcast. Although for broadcast we have lower bound, but for consensus we don't. So what we're looking at in this paper is whether those two problems have equivalent complexity or if there is some gap between them. Now let me tell you a bit more about the specific models in which we examine this problem, because there are already lots of different and definitely non-equivalent ways in which communication can be modeled. So we looked at models where every node chooses just one neighbor to communicate with. So those are called gossip models. Now, once this choice is made, there are still a few interesting variants. So in the push model, every node chooses a neighbor and then sends some information to the neighbor. One node can be chosen more than once, so every node might receive more than one message, but every node sends only one message. In the pull model, every node chooses a random neighbor, and then it's going to ask for a message from that node. So in this case, every node receives only one message, but some nodes may be picked several times, so they will be asked to send multiple messages. The general gossip model, once these communications are established, messages can be exchanged in both directions. Okay. So what about broadcast? There is really kind of only one algorithm for broadcast in the simple models, which is that sort of whenever you are allowed to communicate, if you know the information from the broadcast node, you send it over. Otherwise, you say that you don't know. And then the number of rounds that it will take for the broadcast information to reach all the nodes can be measured by thinking about this infection process, in which initially the only node that knows the broadcast information is the start node. And then at every step, if you receive a message from a node that is infected, from a node that knows, then you are infected and you know the information. So just for both for upper and lower bounds, the analysis just comes down to, well, if you have this process where every node that is infected pushes information infects another, or every node pulls from a random node and gets an infection if the pull node is infected, how long does it take for things to spread? And for example, in a click, the answer is precisely log n. And actually for every graph, it's at least log n. Okay. For general graphs, it relates to the mixing time of the graph, and it's a very well-studied problem. For consensus, there are algorithms that take order of log time in a click. In general, there are algorithms that match whatever is the performance of broadcast in every graph. But we didn't have any, sorry, I wrote superlinear, what I meant was super constant. We didn't have any super constant round lower bounds for consensus. It wasn't clear that you couldn't do it in 3 rounds or 5 rounds. Okay. So our first result is that essentially that every consensus protocol kind of gives a broadcast protocol, or at least as an implication that transfers all the known lower bounds from broadcast. So specifically, what we argue is that if we have a consensus protocol that works, then there is some initial data for the vertices and some vertex, such that if you follow what the exchanged messages look like in this consensus protocol, the start vertex infects all the others. So by the end of the protocol, every vertex has talked to someone, who's talked to someone, who's talked to someone, who has talked to the start node. And so we know how long it takes for infection protocols to reach all the nodes, and it's at least log n in all graphs. In particular, it's at least log n in the click. So the log n is tied for the click. Here, the reason is that, I guess the simplest way to think about this is that suppose you just have two parties and they don't talk. Then it's impossible to do consensus, because imagine the network is just me and Stefano, but we don't talk. So if we both have 0 as an input, we must output 0. So from my point of view, this says if my input is 0, I have to output 0. If we both have input 1, we must output 1. So again, from my point of view, if my input is 1, I have to output 1. Now imagine that I have input 0 and Stefano makes the same reasoning. Imagine I have input 0, Stefano has input 1. I'm going to output 0, it's going to output 1, and the consensus is not reached. Okay. So then if you have nodes that sort of are not infected by one another, it means that their output is independent of the input of the other node, and more or less the same argument can be repeated, and you're going to see an inconsistency. For so our second result, it's about so a similar model, but where communication can include errors, and also where every message is of constant or even 1 bit length, so that you cannot apply error correcting codes to those messages, and so just repair the errors in each communication. So what's happening in this setup is that every node gets a random neighbor and then gets some noisy information from that random neighbor, and then never talks again to that random neighbor except maybe after order of n steps. So then it's very difficult to kind of keep information consistent when you don't have repeated communication between the same two parties, and where each communication has this kind of noise. And in fact, Boczkowski, Natale, Fannerman, and Corman proved that in the pool model, to do broadcast, it requires omega of n rounds. And the reason is that, so that every time a node that knows the information gets it pulled, the recipient gets something noisy. But also, when a node that doesn't know the information gets pulled, has to send something that is also noisy, and becomes difficult to distinguish between having gotten something random from someone who doesn't know anything and getting something noisy from someone that knows something. And so they're able to prove these omega of n lower bounds. Keep in mind, every step, n communications are taking place. So this is n square bits of communication that are necessary. However, in the same model of pool with errors and constant bit messages, we can show that consensus can be done in order of log n steps. So just as long as it takes roughly for the infection to take place. So in summary, we studied consensus and broadcast in these models where every node communicates with only one neighbor, either by pushing or pulling information. If the communication is noiseless, we establish the first super constant lower bound for consensus and show that in a click it matches the tight of log n communication that we know for broadcast. In a noisy case, we show that consensus can still be done in a click with order of log n communication, even though in this case it creates an exponential gap with the complexity of broadcast. Okay, I think I'll stop here. Thanks a lot.
Right, so any questions? And again, usual thing, next speaker, please sit up. So are there obvious generalization of the noisy model, or is it? Are there obvious generalizations of the noisy model that are interesting? I mean, it's natural to have this one bit and sort of binary symmetric channel.
Yeah, well, if you have log n bits, then you can apply error correction.
Right. Thank you. Let's thank Luca. Or not. All right, so next speaker is going to be Ihan, who's going to talk about list decoding.
Okay, so I'm Ihan. I'm going to talk about generalized list decoding. This is a joint work with Amit Butkuli from IIT Kharagpur and Siddharth Jaggi from CUHK. I'm also from CUHK. So let me start gently. What is this? This is a packing. So the black box represents F2 to the n associated with a Hamming metric. And there are many balls inside it, many balls of radius n times p for some number p between 0 and 1, and they are disjoint. So if you take the centers of these balls, they form an error-cutting code, by which I mean, so every pair of points are separated by certain distance. So how many balls can you pack in this Hamming space? So it's known that you can pack exponentially many points as long as p is not too large. But we don't know what the number is, but we do know that as long as p is at most 1/4, you can pack exponentially many points. But how, what the exponential is not known. But we do know the threshold is 1/4. So now I'm going to relax this problem. Instead of requiring that these balls are disjoint, I allow overlap, but with bounded multiplicity. For example, so each point in the space can only lie in the intersection of at most 2 balls in this case. So I call this a 2 packing. So what's the threshold now? So for what value of p can you pack exponentially many points satisfying this so that they form a 2 packing? So in this case, it's also known that the threshold is again 1/4. I can keep relaxing it, right? I can ask, what about 3 packing? The threshold is now changed to 5/16. For 4 packing, it's still 5/16. For 5 packing, it's 11/32. For 6, it's 11/32. I'm not going to continue, but you might have seen the pattern. So it jumps every 2 times. So this is indeed characterized by an early work by Blinovsky. So an exponential sized L-1 packing exists for L being 2k or 2k plus 1, if and only if p is less than this threshold, less than this complicated formula. You see that if you increase L from 1 to some large number, this threshold is going to increase from 1/4 to 1/2. Okay, so what I'm going to do in the rest of the talk is going to significantly generalize this theorem. So this packing problem corresponds to certain communication problem in coding theory. It's called list decoding for against adversaries. So the typical setting is the following. So Alice encodes some message into some code word X and sends it into some channel and is corrupted by some adversary, and the Bob receives some noisy word, and he's required to output some list of messages, not necessarily unique, but some small list of messages, which is guaranteed to contain the original one, the originally transmitted one by Alice. So this is the list decoding relaxation of the unique decoding problem. And this, for binary channel, this is just, every vector in this system is going to be binary. The input of the channel X is binary, and the output of the channel Y is also binary. And the noise vector S, it's required to have Hamming weight at most MP, the same P as before, where P is the radius of the Hamming ball. And the decoder is going to output some list of size at most L, which contains the transmitted M. So generally, this channel can be made, there's a much more general model in information theory, namely the following. So I can make every vector in the system to come from a general alphabet. For example, X is coming from general script X to the N, Y is from script Y to the N. The noise vector S is from script S to the N. And I want the input to the channel X and S to satisfy certain constraints. In the binary space, in the binary case, the S has to satisfy some Hamming weight constraint. But here, the way I impose constraints is in terms of the type of a vector. So what is a type? It's nothing but the histogram of a vector. So for example, if you have some ternary vector x, it looks something like this. And the type of x is just its histogram. Maybe 0.3 fraction of it is a, 0.2 fraction of it is b, and so on. So the type of it is just a probability distribution in some sense. So in general, if you have multiple vectors, for example, 2 vectors, and they jointly look like this, then their joint type is going to be a matrix, right? So how many fractions of AA are there in x and x prime? How many fractions of AB are there in x and x prime? And so on. So in general, if you have L vectors, the joint type of them is going to be an L tensor, right? So now the way I impose constraints onto the input of the channel is going to be defined as the following. So the input of the channel is, let's first look at x. I require that its type has to lie within certain subset of types. Let's say the type of x, tau x, has to lie within lambda x. It's a subset of the probability distribution, of the probability simplex. Okay, similarly, so for x, I define some lambda s, is the type constraint. I want its type to lie within lambda s. Again, type is just a histogram. So now, again, the goal for the communication is to decode to a small list of messages which contain the truly transmitted one. So for this general setting, of course, it covers the binary channel and also many other channels, but it excludes the insertion-deletion channel because I require the channel to act on the inputs component-wise. That's not, it cannot capture the insertion-deletion channel, unfortunately. So first observation, if I only care about the positivity of the rate, namely, if I only care about when can I pack exponentially many points, but I don't care how many points can I pack, then I can work with constant type code. Because given any code, you can extract the constant type code of the largest size, right? One thing to note is that for length n vectors, there are only polynomially many types you can count. It's a simple question. So now we're in the position that I can state our theorem. So to do that, I need 3 definitions, 3 sets in particular. So the first thing is, so let's fix any allowable distribution that can be fed into the channel, let's say px. It represents certain type of a code word. The first set is a set of distributions which I call self-coupling. It's a set of distribution px1 to xl such that if you marginalize onto any xi, it's going to be equal to some given px, which I fixed in advance. I call it self-coupling. I'm not sure if it's standard, but anyway. The second one is the most crucial one for the theorem. Let's say you have 3 vectors, x1, x2, x3. They are said to be confusable if there are some adversarial noise vector s1, x2, s3, which send them to the same y under the action of the channel, right? Then they are going to be confusable under this s1, s2, s3. So I want to, this is also permutation invariant because the channel is component-wise. So now I want to define the following distribution. It looks complicated, but it's the set of distribution px1 to xl. You should think it as the type induced by L tuple of vectors, L tuple of code words, such that they are confusable. What does that mean? That means that if it comes from certain extension of distribution, px1 xl and s1 sl and y, so that if you marginalize onto x, it's consistent with the given x1 to xl. If you marginalize onto s, it's allowable. Namely, it corresponds to a type of a noise vector. And it's also consistent with the channel law. Namely, it decomposes as the following. It's equal to px1, px, ps given x, wy given xs. So it's consistent with the channel. So these set of distributions are bad in the sense that I want to avoid it. A good code should not contain a couple of code words so that they induce any distribution that lie within this confusability set. So this is a bad distribution set that a code should avoid. So finally, this is a technical thing, completely positive tensor cone. It's a set of distribution which can be decomposed into the convex combination of a bunch of rank 1 distributions. So why is this useful? Because it can be shown that via random coding, so for any given channel, J, the set of self-coupling is always there, and K you can compute, it's associated to some channel. If you can find some distribution outside K, then you can sample from that distribution a code so that it's good for list decoding. It's not confusable. So the way you do it is just a sample from that distribution Px, each component independently. And you can slightly generalize this. If the independent distribution Px tensor L is not outside K, but you can find some distribution Px1 to xl which is completely positive. Namely, you can decompose it into a convex combination of a bunch of rank 1 distribution. Then you can again sample a code. Maybe in the first 5 columns, if you sample from distribution Px given 1. In the second 10 columns, you sample from distribution Px given 2, and so on. This is again going to work if the convex combination of this distribution is outside of the confusability set. Right? Because again, the confusability set is bad. I want to avoid it. Now, from the positive side, if CP is not completely contained in K, then there exists exponential sized code. And what I want to show you is that the converse is also true. If CP is completely contained in K, then there's no way to construct a large least decodable code. And the proof makes use of duality between CP and copy and so on. And it's a generalization of the blocking bound. And that's basically it. I don't have enough time to talk about the details, so you can refer to this reference. So yeah, that's our theorem. That's it. Thank you.
Just again, we are running late, so maybe I suggest pushing the questions to the break unless there's a quick one. And then next speaker, final speaker, you can sit up. Fault-tolerant subgraphs now.
Yeah, replication in canalization. All right, so let's start with fault-tolerant subgraph. So the setting is the following. So we have a digraph D, 2 subset of vertices of D, and an integer K, and the goal is to find a subgraph H, so that whenever we remove at most K arcs, so this is the set F from this graph H, and you take one vertex in S and one vertex in T, then there exists a path from S to T in D minus F, if and only if there exists a path from S to T in H minus F. So here the intuition is you want to remove as much information possible from the graph, but you want to preserve the information of connectivity between S and T, even if you have K arcs which fails. Okay, so you remove them. So this was introduced in 2016 by Pasquale et al. And so in this paper, they also show that if you take S to be a single vertex and T to be the full vertices of the digraph, then the number of arcs you need is basically 2 to the K times N. Okay? So they also show that this set H can be found efficiently, and also that this is like the best possible size. So the question that we ask in this paper is, okay, can we remove or can we decrease this dependency on N? So of course, in the case of Pasquale theorem, the set T is the full graph, so you need to remember at least every vertex, so this is not possible. But maybe for some other situation, this is possible. And the easiest of all is what happens when S is a single vertex and T is a single vertex. So in particular, what we look at here is we want to remove completely the dependency on N. So we want something that only depends on K and maybe some other parameter. Okay. So this is a very bold question, and let's see some trivial cases where this is not possible. So first, suppose that your graph D is just a path from S to T. Then obviously you cannot remove anything here, because if you remove anything, you disconnect these 2 points, and this is not allowed. So somehow, some notion of density would be, seems to be necessary. But even that is not enough, because basically you can cheat and adapt this example by just putting all the arcs possible, but in the reverse order of your path. And again, so this gives you a tournament, so an orientation of the clique. And here, if you remove any vertex between S and T, you disconnect these 2 points. Okay. So, all right. So these are trivial lower bounds, but let me show you an example where this works. And the proof is not very difficult. Suppose now D is a transitive tournament. So what we call transitive tournament is just a tournament without any directed cycle. So the best way to look at these tournaments is just you have an enumeration of the vertices, which is represented here, and all the arcs go into the same direction. Right. And what I claim is that if D is transitive tournament, then this fault-tolerant reachability problem has a solution of size k plus 2. All right. So how does it work? Well, it's not very hard. So the first thing is you look at the places of the vertices S and T in this ordering. And then you realize that every vertex before S and every vertex after T does not belong to any path between S and T. So you can remove them safely. And then you have 2 cases. So if there is less than k vertices between S and T, you're happy. So basically you keep all of the vertices. And you know that this is of size smaller than k plus 2. And the other cases is when there is more than k vertices between these 2 vertices. And in that case, there is no k arc cut. And basically, this is the only information that you need to remember, that there is no k arc cut between S and T, but for this, you only need to keep k vertices. All right. So the main result of this paper is to try to extend this proposition, basically. This is a proposition. Okay, so how do we generalize this? Well, first we need to generalize tournaments. And here, so probably the most natural way of generalizing tournaments is to look at the independence number of the digraph, where the independence number is just the size of the largest set without any arcs. And d alpha will denote the class of digraph with independence number smaller than alpha. And this is a generalization of tournaments because tournaments is just the case alpha is equal to 1. Okay? And so the main result is the following, is that basically we can prove a similar result when D belongs to the class of D alpha. And actually we'll generalize it a bit more because before that, so I showed you the acyclic case, and what we say is that, okay, we don't need it to be acyclic, but the strongly connected component needs to be small or bounded. And if this is the case, then you have a solution to the FTRST problem of size, okay, this thing, so KL to the 4L alpha squared. Yeah, so this is the main theorem, and I don't want to talk about the proof so much. It's quite technical, as the bond probably suggests. It's basically a proof by induction on alpha, and the main trick is to use vertex cut to reduce the independence number of the graph you consider. Right. Okay, so this is what happened for fault tolerance, and now I will show you how we can use this result to obtain some result in kernelization. Yeah. So first, let me define a bit what is a polynomial kernel. So we're in the world of parameterized complexity. So a problem P as a polynomial kernel, if there exists a polynomial time algorithm which transforms any instance ik of this problem into an equivalent instance I prime k prime with the following property that basically the size of a prime plus k prime is a polynomial function which only depends on k. And here the idea is basically to identify the hard part of the problem in polynomial time, and we can show that the hard part is somewhat restrained. So one of the nice questions about the existence of polynomial kernel is the one concerning directed feedback arc set problem. So here, probably you know this one, but let me just say it again. So you have a digraph D and an integer k, and the goal is to answer the question, can we remove k arcs in order to make D a cyclic? Okay. So this is a well-studied problem, and in particular, we know that there is an algorithm in f of k to the n squared, so FPT algorithm, and this is due to Chen in 2008. And since then, the question of the existence of a polynomial kernel for the dialectic feedback arc set remains open. And this is quite a nice question, but unfortunately, we don't know so many things about it. The one thing we do know about is that for the tournament case, this is known. And actually, anybody introducing the notion of polynomial kernel would probably start with this example. So this is like the textbook example for the existence of polynomial kernel. And okay, so now you see me coming. What we're trying to do is generalize these results on the class of bounded independence number diagram. Okay, and this is the theorem that we prove. Here is that dialectic feedback arc set admits a polynomial kernel on this class of diagram. So generalizing this result. And in the few minutes that I have left, let just me tell you a bit how we can use this fault-tolerant reachability solution in order to get this kernel. So now you have a digraph D, and you try to remove k arcs to make a cyclic. And one nice thing about D being a bounded independence number is that if you have a cycle, you have a short cycle. So this is not very hard to see. If you have a long cycle, then there is a chord, basically just by because the independence number is bounded. And if you have a chord, then basically you get a shorter cycle. So what this allows us to do is you can now greedily pick small cycles, so cycle of size 2 alpha plus 1, which are disjoint, so you get the maximal packing if you want. And then you have two cases. So either you find more than k disjoint cycles. Okay, in that case, the answer to your question is no, because you have to take at least one arc in each cycle. Or you find a set S of 2 alpha plus 1 times k vertices, so that D minus S is a cyclic. And so this is very nice for us, because now that you have found this set S, basically every vertex which is outside of S is just there to connect the vertices of S. Okay? So we want to find a kernel, so basically we want to reduce the instance, and what we want to do is reduce the size of the vertices, reduce the size of the vertices outside of D minus S, while maintaining the important information about this set. And as I said, the important information about this set is just the connectivity between the vertices of S. So basically what we just want to do now is keep enough information outside of S to understand the cost of disconnecting some pair of vertices between of S. Right. So more formally, this will be the kernel. So you take H to be the solution of the k fault-tolerant reachability problem between S and S. And then D prime is the digraph induced by D on S union H. So all of these vertices. And what I claim is that D prime K is the kernel. So it's the reduced instance, and the size of it is basically K to the 4 to the alpha squared. Okay. And so how do we prove it's a kernel? Well, first, we have to show that these two instances are equivalent. So since D prime is a subgraph of D, if dk has a solution, D prime k also has a solution. And now the question is, what's the reverse direction? So actually what we can prove is that for any f of size less than k, if D minus f has a cycle, then D prime minus f has 1. And the proof is here. So suppose you have a cycle C in D minus f. So we know that this cycle intersects S. This is the definition of S. So let's say, for example, we have these 3 points, and then basically we have a path from S1 to S2, a path from S2 to S3, and a path from S3 to S1 in D minus F. But now, by definition of this fault-tolerant reachability problem, it means that in D prime minus F, we also have a path between S1 and S2, S2 and S3, S3 and S1, etc. And thus, we have a closed walk in D prime minus F, and thus a cycle. Right. So this is the kernel, and let me finish with some conclusion. So first, So actually what we can do is we can do something a bit stronger than what I showed you, is that we can show that the problem of finding an eating set for the cycle of length 1 mod p admit a polynomial kernel on D alpha. And here the 1 is very important. Okay, so it doesn't work for any other value here. So this is quite strange. And then let me just ask you 2 questions. So the main ingredient for this solution of the fault theorem integrability problem is that in D alpha, you don't have any induced paths of length 2 alpha plus 1. Okay, so this is just because you have a chord between them. And our question is, okay, can we adapt everything that we just did in the case of P alpha 2 alpha plus 1 path 3, and this will give you the kernel for this class of graph, which will be also nice. And finally, let me repeat our first question is, so we showed, one case is where this problem admits a solution which is independent on n, but what happens when you ask for log n or for square root n, which are easier, so probably the classes of digraph where you can have such a result might be a bit more, say, bigger than just a very restricted one that we just look at. Thank you very much.
Is there a very urgent, quick question? Otherwise, I suggest we move on to get coffee, and we have break until 11:30. And you can ask questions in the break. But let's thank all of the speakers of the first session.